When we gaze up at the night sky, we see thousands of stars scattered across the darkness. But what we're witnessing is just the tiniest fraction of an incomprehensibly vast cosmos. Beyond those twinkling points of light lies an ocean of space so immense that our minds struggle to grasp its true scale. Yet even this observable universe, containing hundreds of billions of galaxies, each with billions of stars, represents only a small bubble of everything that exists. What lies beyond the edge of what we can see? Is there truly an infinite expanse of space stretching endlessly in all directions? Or does the universe have boundaries we cannot yet comprehend? Join me as we venture into the deepest mystery of existence itself, the question of what lies beyond the edge of everything we know. The observable universe is not the entire universe. It's simply the portion from which light has had enough time to reach us since the Big Bang. This creates a spherical boundary around us, approximately 93 billion light-years in diameter, beyond which we cannot see. This boundary exists not because the universe ends there, but because we are limited by the speed of light and the age of the universe. Think of it like standing in a vast desert at night with only a flashlight. The circle of light around you represents everything you can observe, but the desert extends far beyond what your light can illuminate. Similarly, the observable universe is our cosmic flashlight beam, illuminating only a small region of what may be an infinite expanse. This observational horizon creates a profound isolation. Galaxies beyond this boundary are forever hidden from us, their light unable to bridge the vast distances in the time since the universe began. As the universe continues to expand, this horizon grows, but paradoxically, galaxies currently at the edge will eventually disappear from view as space itself carries them away faster than their light can reach us. The cosmic microwave background radiation, the afterglow of the Big Bang, forms the most distant observable phenomenon, showing us the universe as it was just 380,000 years after its birth. This radiation comes from every direction, forming a wall beyond which we cannot see, not because nothing exists there, but because the universe was opaque to light before this time. Understanding this boundary is crucial because it defines the limits of empirical science. Everything we know about the universe, from the laws of physics to the distribution of galaxies, comes from observations within this cosmic bubble. Beyond this boundary lies terra incognita, an unknown realm that may contain wonders beyond our imagination or may simply be more of the same. The mathematics of our cosmic horizon reveal disturbing truths about isolation. Every second, space expands by roughly 70 kilometers per second per megaparsec of distance. This means that galaxies at the edge of our observable universe are receding at nearly the speed of light. Beyond a certain distance, they recede faster than light can travel toward us, creating an absolute barrier to observation. This cosmic event horizon is not fixed, but evolves over time. As the universe ages, light from more distant regions has time to reach us, slowly expanding our observable bubble. However, the accelerating expansion driven by dark energy means that galaxies currently visible at the edge will eventually cross into the unreachable realm, disappearing forever from our view. Within our observable sphere, we can count approximately 2 trillion galaxies, each containing an average of 100 billion stars. This gives us roughly 200 sextillion stars within our cosmic neighborhood, a number so large it exceeds the grains of sand on all Earth's beaches. Yet this incomprehensible multitude represents merely the visible portion of what may be an infinite cosmos. The implications of our cosmic imprisonment are profound. We can never know with certainty whether the laws of physics we observe locally apply throughout infinite space. We cannot determine whether life exists elsewhere by direct observation beyond a certain distance. We cannot even confirm whether the universe is homogeneous on the larger scales or contains vast regions with dramatically different properties. This limitation haunts every cosmological theory and every attempt to understand our place in existence. We are like intelligent microbes confined to a single drop of water, trying to understand the nature of the ocean that surrounds us. The ocean may be infinite, but we can never know for sure. If the universe is infinite, then beyond our observable horizon lies more space, endless space, containing more galaxies, more stars, more planets, and potentially more life than we could ever catalogue. In an infinite universe, every possible arrangement of matter would not only exist but would be repeated infinitely many times. This means that somewhere beyond our view, there could be exact duplicates of our solar system, our planet, and even ourselves. The mathematics of infinity produce mind-bending implications that challenge our most basic intuitions about reality. Mathematicians have long grappled with the concept of infinity, discovering that it behaves in ways that seem to violate common sense. When we apply these mathematical insights to cosmology, the results are both thrilling and terrifying. Consider the following thought experiment. In a finite but extremely large volume of space, there are only a finite number of ways to arrange a finite number of particle types. Even if this number is unimaginably vast, say 10 to the power of 10 to the power of 100, it remains finite. In an infinite universe, every possible arrangement must occur, and each must occur infinitely many times. This leads to the shocking conclusion that in an infinite universe, there are not only other Earths, but infinitely many of them. Some would be identical to ours down to the quantum level, while others would differ by just a single particle's position. There would be Earths where dinosaurs never went extinct, where you chose a different career, where World War II never happened, and where the laws of physics operate with slightly different constants. The mathematician's concept of countable versus uncountable infinity becomes relevant here. If space is infinite but matter is distributed with finite density, then the number of particles in the universe would be countably infinite, vast beyond comprehension, but still a smaller infinity than the uncountable infinity of real numbers. This suggests that while there would be infinite copies of every possible arrangement, some arrangements would be infinitely more common than others. The pigeonhole principle, a basic mathematical concept, takes on cosmic significance in infinite space. If you have infinite objects distributed among finite categories, then infinitely many objects must fall into each category. Applied to cosmology, this means that in infinite space with finite types of matter and energy, every possible cosmic structure must occur infinitely often. But infinity produces paradoxes that strain human logic. In an infinite universe, does it make sense to ask which galaxy is typical? Every galaxy, no matter how unusual, would have infinitely many twins. The rarest cosmic phenomena would still occur infinitely often. Statistical concepts like probability and frequency begin to break down when dealing with infinite sets. Cantor's diagonal argument, which proves that there are different sizes of infinity, suggests that even if space is infinite, there might be even larger infinities at play. The number of possible universes might be a larger infinity than the number of locations in infinite space, meaning that even infinite space couldn't contain every possibility. The mathematical concept of measure theory becomes crucial when discussing infinite cosmology. Even in infinite space, we can ask about the density or measure of different types of regions. Perhaps regions like our observable universe have measure zero in the infinite whole, making us infinitely rare despite existing infinitely often. Set theory reveals another puzzling aspect of cosmic infinity. In infinite space, every possible subset of matter arrangements exists infinitely often. This includes subsets that seem to violate causality or physical law, regions where entropy decreases, where time appears to flow backward, or where the normal rules of physics break down entirely. The mathematical study of infinite series and convergence becomes relevant to questions about energy and matter distribution in infinite space. Does infinite space contain infinite energy? If so, how do we understand conservation laws? These questions push the boundaries of both physics and mathematics. Gödel's incompleteness theorems suggest that even perfect mathematical systems contain statements that cannot be proven within the system. Applied to infinite cosmology, this might mean that there are truths about infinite space that can never be verified or falsified by any possible observation or logical argument. The concept of multiple universes, or a multiverse, suggests that our entire cosmos might be just one bubble in an infinite foam of universes. This idea emerges from several areas of theoretical physics, each proposing different mechanisms for how multiple universes could exist and interact. Eternal inflation theory provides perhaps the most compelling scientific framework for understanding the multiverse. According to this theory, the rapid expansion that followed our Big Bang never truly stopped everywhere. While inflation ended in our region of space, creating the relatively calm, expanding universe we observe today, it continues in other regions, constantly creating new pocket universes. The mechanism behind eternal inflation involves quantum fluctuations in the inflaton field, the hypothetical field responsible for cosmic inflation. In most regions, these fluctuations cause inflation to continue indefinitely. Occasionally, however, the field decays to a lower energy state, ending inflation and creating a bubble universe like ours. This process repeats infinitely, generating an endless cascade of new universes. Each bubble universe born from eternal inflation would be causally disconnected from all others, existing in its own region of space with potentially different physical laws, constants, and properties. The space between bubbles continues to inflate exponentially, ensuring that they never collide or interact. From our perspective within our bubble, these other universes are not just unobservable, but fundamentally unreachable. The landscape theory from string theory provides a framework for understanding how different universes could have different physical properties. String theory suggests that our familiar three spatial dimensions are just a small part of a higher dimensional space. The shape and size of these extra dimensions, along with various field configurations, determine the apparent physical laws and constants in each region. With an astronomical number of possible configurations, estimates suggest 10 to the power of 500 or more distinct possibilities. The string landscape could populate the eternal inflation multiverse with universes spanning every conceivable type of physics. Some would have gravity so strong that matter cannot form stable structures. Others would have electromagnetic forces so weak that atoms cannot hold together. A tiny fraction would have conditions suitable for complexity and life. The many worlds interpretation of quantum mechanics provides another pathway to multiple universes. According to this interpretation, every quantum measurement that could go multiple ways actually does, splitting reality into parallel branches. This creates an ever-branching tree of universes, each containing a different outcome of every quantum event that has ever occurred. In the many-worlds scenario, the number of parallel universes grows exponentially with each quantum measurement. Every radioactive decay, every photon interaction, every decision made by conscious beings splits the universe into multiple copies. The total number of parallel worlds becomes unimaginably vast, containing every possible history consistent with quantum mechanics. These quantum parallel universes differ from eternal inflation bubbles in crucial ways. While inflation creates separate spacetimes with potentially different physical laws, quantum many-worlds creates parallel versions of the same spacetime with identical laws but different histories. In one branch, Schrödinger's cat lives. In another, it dies. In one branch, you become a scientist. In another, an artist. Ekpyrotic and cyclic cosmological models suggest yet another type of multiverse. These theories propose that our Big Bang was not the beginning of everything, but just one event in an eternal cycle. The universe expands, contracts, and then bounces back in a new Big Bang, potentially with different physical constants each time. In the ekpyrotic scenario, our three-dimensional universe exists as a membrane, or brain, in higher dimensional space. Other brains could exist parallel to ours, and when they collide, they create the explosive events we interpret as Big Bangs. This process could repeat infinitely, creating an endless sequence of universe generations. The mathematical universe hypothesis, proposed by physicist Max Tegmark, suggests that all mathematical structures exist as physical realities. Since mathematics contains infinitely many possible structures, this would imply infinitely many universes corresponding to every consistent mathematical framework. Our universe would simply be one mathematical structure among infinitely many others. This mathematical multiverse would contain not just universes with different physical constants, but universes with entirely different mathematical foundations. There would be universes based on non-Euclidean geometries, universes where numbers behave differently, and universes governed by mathematical structures we haven't yet discovered. The anthropic principle gains new significance in multiverse scenarios. Rather than wondering why our universe seems fine-tuned for life, we can understand it as a selection effect. In a multiverse containing every possible type of universe, conscious observers like us naturally find themselves in universes capable of supporting consciousness. The vast majority of universes would be sterile, but we cannot observe those from the inside. However, the multiverse concept faces serious criticisms from some scientists and philosophers. The primary objection is that multiverse theories are untestable. If we can never observe other universes, how can we know they exist? This pushes the theories beyond the realm of empirical science into speculation. Furthermore, the multiverse may not solve the problems it was designed to address. If there are infinitely many universes, then fine-tuning problems simply move to a higher level. Why do the laws governing the multiverse itself permit universe-generating mechanisms? The question of ultimate origins remains unanswered. Despite these criticisms, multiverse theories continue to attract serious scientific attention because they emerge naturally from our best theories of physics. Eternal inflation follows from relatively simple assumptions about scalar fields in the early universe. Many worlds' interpretation solves the measurement problem in quantum mechanics. String theory landscape provides a mathematical framework for different vacuum states. While we focus on what lies beyond our observable universe, it's sobering to realize that we don't understand most of what exists within it. Dark matter and dark energy, which together comprise about 95% of the universe, remain largely mysterious despite decades of intensive research. Understanding these invisible components is crucial to understanding what might exist in the vast regions beyond our observation. Dark matter reveals itself only through its gravitational effects, yet these effects are profound and unmistakable. It forms vast scaffolding throughout the universe, creating the cosmic web along which ordinary matter flows to form galaxies and stars. Without dark matter, galaxies would fly apart, unable to hold themselves together through gravity alone. The orbital velocities of stars in galaxy outskirts remain high even at large distances from the galactic center, indicating the presence of much more mass than we can see. Galaxy clusters provide some of the strongest evidence for dark matter. These massive collections of galaxies containing thousands of individual stellar systems move too fast to be held together by the gravity of visible matter alone. The hot gas between galaxies in clusters also provides evidence. Its temperature and distribution can only be explained if much more mass is present than what we observe directly. Gravitational lensing offers another window into dark matter's distribution. Massive objects bend light according to Einstein's general relativity, and we can observe this bending effect even when the massive object itself is invisible. Dark matter concentrations create gravitational lenses that distort the images of background galaxies, allowing us to map dark matter's location and estimate its mass. Current theories suggest dark matter consists of exotic particles that interact very weakly with ordinary matter and electromagnetic radiation. These particles could be streaming through your body right now by the billions without you ever knowing. The leading candidates include axions, extremely light particles predicted by certain extensions of the Standard Model, and weakly interacting massive particles, WIMPs, that could be hundreds of times heavier than protons. Sterile neutrinos represent another dark matter candidate. These hypothetical particles would be similar to the known neutrinos that flood the universe, but would interact even more weakly with ordinary matter. Primordial black holes formed in the early universe could also contribute to dark matter, though current observations limit how much of the dark matter budget they could comprise. The search for dark matter particles involves sophisticated underground detectors shielded from cosmic rays and other interference. These experiments look for the rare occasions when dark matter particles might collide with atomic nuclei in the detector material. Particle accelerators like the Large Hadron Collider also search for dark matter by creating conditions similar to those in the early universe, hoping to produce these elusive particles in high-energy collisions. Dark energy presents an even greater mystery. Comprising about 68% of the universe, it appears to be causing the accelerating expansion of space itself. Unlike dark matter, which clumps and forms structures, dark energy seems to be smoothly distributed throughout space, growing stronger as the universe expands. The discovery of dark energy came from observations of distant supernovae in the late 1990s. Type Ia supernovae serve as standard candles because they all have similar intrinsic brightness. By comparing their apparent brightness to their expected brightness, astronomers can determine their distance. These observations revealed that distant supernovae were fainter than expected, indicating they were farther away than predicted by models without accelerating expansion. Several theories attempt to explain dark energy's nature. The cosmological constant represents the simplest explanation, a property of space itself that remains constant as the universe expands. Einstein originally introduced this constant to keep his equations consistent with a static universe, later calling it his greatest mistake when Hubble discovered cosmic expansion. The discovery of accelerating expansion has rehabilitated the cosmological constant as a viable explanation for dark energy. Quintessence theories propose that dark energy is a dynamic field that changes over time, similar to the inflaton field thought to drive cosmic inflation. Unlike the cosmological constant, quintessence would evolve as the universe expands, potentially strengthening or weakening over cosmic time. This could lead to different fates for the universe than constant dark energy would produce. Modified gravity theories suggest that our understanding of gravity itself breaks down on cosmic scales. Rather than invoking a new form of energy, these theories propose that general relativity requires modification at the largest scales. The observed acceleration could result from gravity behaving differently than expected rather than from a mysterious energy component. The phantom dark energy scenario presents a disturbing possibility where dark energy strengthens over time. In this case, the acceleration of expansion would increase until it overcomes all other forces, eventually tearing apart galaxies, stars, planets, and even atoms themselves in a big rip ending to the universe. Dark energy's smooth distribution raises questions about its relationship to space itself. If dark energy is truly a property of the vacuum, then as space expands, more space is created, and with it, more dark energy. This would create a positive feedback loop where expansion creates more dark energy, which drives more expansion, creating even more dark energy. The coincidence problem in dark energy research asks why dark energy became dominant just as complex structures like galaxies and life were forming. For most of cosmic history, matter dominated the universe's energy budget. Only in recent cosmic time did dark energy take over. This timing seems suspiciously convenient for the existence of observers like us. Quantum field theory predicts that empty space should contain vacuum energy, which could contribute to dark energy. However, naive calculations give a vacuum energy density that is 120 orders of magnitude larger than observed. This cosmological constant problem represents one of the worst predictions in the history of physics and suggests that our understanding of vacuum energy is fundamentally flawed. The existence of dark matter and dark energy raises profound questions about the nature of reality beyond our observable universe. If we cannot directly detect 95% of what exists in our own cosmic neighborhood, what hope do we have of understanding what lies beyond? These invisible components might behave differently in other regions of infinite space, creating environments with entirely different structural and evolutionary possibilities. In regions where dark matter is more dense, galaxy formation might proceed more rapidly, leading to earlier development of complex structures and potentially life. Areas with different dark energy densities could experience different expansion rates, creating pocket universes with varying degrees of structure formation and stellar evolution. The relationship between dark matter, dark energy, and the fundamental constants of physics remains unclear. In other regions of infinite space or other universes within a multiverse, these components might take different forms or have different effects. This could lead to cosmological environments we cannot imagine based on our limited local experience. On the grandest scales, the universe resembles a vast web of filaments connecting dense nodes where galaxies cluster. This cosmic web structure extends throughout the observable universe and presumably continues beyond our horizon into whatever lies in the infinite darkness. Understanding this architecture provides clues about how matter organizes itself on the largest scales and what structures might exist in the unreachable regions of space. The cosmic web formed from tiny density fluctuations in the early universe, amplified by the gravitational attraction of dark matter over billions of years. These microscopic variations in density, imprinted during cosmic inflation, grew into the largest structures we observe today. Galaxy clusters connected by filaments of dark matter and gas, separated by enormous voids containing very little matter. Computer simulations of cosmic structure formation reveal the web's intricate beauty. Dark matter forms the scaffold, creating a network of intersecting filaments that span hundreds of millions of light years. Ordinary matter flows along these filaments like water through a circulatory system, collecting at the intersection points where massive galaxy clusters form. The filaments themselves are not uniform structures, but contain complex substructure. Smaller galaxies and galaxy groups flow along these cosmic highways, occasionally merging with larger systems at the intersection points. The flow of matter along filaments helps feed the growth of galaxy clusters and influences the evolution of galaxies throughout cosmic time. Galaxy clusters, the nodes of the cosmic web, represent the largest gravitationally bound structures in the universe. The most massive clusters contain thousands of individual galaxies swimming in an ocean of hot plasma that emits X-rays as it falls into the cluster's gravitational well. This hot gas, heated to temperatures of millions of degrees, outweighs all the visible matter in cluster galaxies combined. The space between cluster galaxies reveals violent cosmic processes. Galaxies plunging through the hot intracluster medium experience RAM pressure stripping, where their gas is stripped away like hair in a cosmic wind. This process can shut down star formation in infalling galaxies, transforming gas-rich spiral galaxies into gas-poor ellipticals. Cluster collisions provide natural laboratories for studying dark matter and the extreme physics of cosmic structure formation. When two galaxy clusters merge, the collision releases more energy than billions of supernovae. The dark matter halos pass through each other relatively unimpeded, while the hot gas crashes together and shocks, creating temperature and pressure waves that can be observed with X-ray telescopes. The most famous cluster collision, the Bullet cluster, provided compelling evidence for dark matter's existence. In this system, the dark matter, inferred from gravitational lensing, separated from the hot gas, observed in X-rays during the collision, proving that most of the mass is in an invisible component that interacts only gravitationally. Between the filaments lie vast cosmic voids, regions where galaxy density is far below average. These voids, often called cosmic bubbles, can span hundreds of millions of light years, so large that a traveller moving at the speed of light would take longer to cross them than the entire current age of the universe. Despite their name, voids are not completely empty, but contain isolated dwarf galaxies and tendrils of gas. The largest known void, the Boötes void, or Great Nothing, spans approximately 330 million light-years in diameter. Within this enormous region, galaxy density is about 10% of the cosmic average. Galaxies within voids often have unusual properties. They tend to be bluer and more gas-rich than their counterparts in denser environments, suggesting different evolutionary histories. Void galaxies provide insights into how environment affects galactic evolution. Protected from the gravitational harassment and gas stripping that occurs in dense regions, void galaxies can maintain their gas supplies longer and continue forming stars at steady rates. They represent cosmic laboratories for studying galactic evolution in isolation. The boundaries between voids and filaments are not sharp, but represent transition zones where matter density gradually increases. These walls and sheets of galaxies form the surfaces of the cosmic bubbles, creating a foam-like structure on the larger scales. The local group of galaxies, which includes the Milky Way and Andromeda, sits on the edge of the local void. Cosmic flows reveal the web's dynamic nature. Galaxies don't just sit statically in the web, but flow along filaments toward the densest regions. Our own local group participates in this cosmic flow, moving toward the Virgo cluster as part of the larger motion toward an even more massive structure called the Great Attractor. The Great Attractor, located behind the dust lane of our galaxy, and thus partially hidden from optical observation, appears to be pulling our local group and surrounding galaxies toward it at speeds of several hundred kilometers per second. However, recent observations suggest that the Great Attractor itself is being pulled toward an even larger structure, the Shapley supercluster, creating a hierarchy of cosmic flows. Dark flows represent motion on even larger scales, suggesting that matter in our observable universe might be moving collectively in response to gravitational attraction from structures beyond our cosmic horizon. If confirmed, these flows would provide indirect evidence for massive structures in the unobservable universe, giving us our first glimpse of what might lie beyond the edge of everything we can see. The web's fractal nature appears at multiple scales. Just as galaxies cluster into groups and clusters, these clusters themselves cluster into superclusters. The Laniakea supercluster, which contains the Virgo cluster and our local group, spans 520 million light-years and contains the mass of 100 million billion suns. Yet even Laniakea is just one part of larger structures in the cosmic web. Supercluster complexes and walls represent structures on the largest observable scales. The Sloan Great Wall, a structure of galaxies spanning over 1 billion light-years, was once thought to be the largest structure in the universe. However, even larger structures like the Hercules Corona Borealis Great Wall, stretching over 10 billion light-years, have since been discovered. These enormous structures challenge our understanding of cosmic homogeneity. Standard cosmological models predict that the universe should appear uniform on scales larger than a few hundred million light-years, yet we observe structures that span significant fractions of the observable universe. This suggests either that our models are incomplete, or that we haven't yet observed on large enough scales to see true homogeneity. The cosmic web's evolution continues today as dark energy drives accelerating expansion. While gravitationally bound structures like galaxy clusters remain intact, the filaments connecting them stretch and thin as space expands. Over cosmic time, the web will become increasingly sparse as expansion carries its components apart. In the far future, cluster collisions will become increasingly rare as expansion carries clusters beyond each other's gravitational reach. The cosmic web will fragment into isolated islands of matter, separated by ever-growing voids. Understanding this evolution helps us predict the universe's long-term fate and the conditions that future civilizations might face. If space extends infinitely beyond our observable horizon, then the cosmic web presumably continues indefinitely. There could be structures even larger than those we observe, superclusters of superclusters, walls spanning dozens of billions of light-years, and voids so large they make our local cosmic bubbles seem small by comparison. The web's continuation into infinity raises questions about its overall geometry and topology. Is the web simply a random network extending forever, or does it have large-scale patterns we cannot observe from our local vantage point? Could there be regions where the web takes entirely different forms, perhaps creating structures we cannot imagine based on our limited observations? Regional variations in dark matter and dark energy could create cosmic web architectures unlike anything in our observable universe. Areas with higher dark matter density might develop more pronounced filamentary structure, while regions with different dark energy properties could experience altered expansion histories, leading to web geometries we have never observed. The cosmic web represents both the largest structure we can observe and our best guide to what might exist in the infinite regions beyond our sight. Its intricate architecture demonstrates how simple physical laws, operating over cosmic time, can create complexity and beauty on the grandest scales. Understanding the web's nature and evolution provides our clearest window into the structural possibilities of infinite space. If space extends infinitely beyond our observable universe, then the question of extraterrestrial life becomes not whether it exists, but how common it is and what forms it might take across the infinite expanse. In an infinite universe, even the most improbable events must occur somewhere, and life could exist in forms we've never imagined, operating on scales both unimaginably vast and incomprehensibly minute. Within our observable universe alone, conservative estimates suggest there are at least 2 trillion galaxies, each potentially containing billions of habitable planets. The sheer scale makes it seem almost impossible that Earth hosts the only life in the cosmos. Yet despite decades of searching with increasingly sophisticated instruments, we have found no definitive evidence of life elsewhere, a puzzle known as the Fermi paradox. The Fermi paradox becomes even more perplexing when considered in the context of infinite space. If the universe is infinite and contains infinite habitable worlds, then it should contain infinite civilizations. Some of these should have developed technology billions of years ahead of ours. Where are they? Why don't we see evidence of their existence in the form of megastructures, altered stellar spectra, or deliberate signals? Several solutions to the Fermi paradox have been proposed, each with different implications for life in infinite space. The rare Earth hypothesis suggests that while simple life might be common, the specific conditions required for complex life and intelligence are extraordinarily rare. In this view, the chain of events leading from simple organisms to technological civilization involves so many improbable steps that it seldom occurs even in infinite space. The Great Filter hypothesis proposes that there's a stage in the evolution from non-life to advanced civilization that is extremely difficult to pass. This filter could be behind us, perhaps the emergence of life itself, or the development of complex cells, or the evolution of intelligence. Alternatively, it could lie ahead of us, perhaps in the transition to a spacefaring civilization, or in surviving the technological risks that come with advanced capabilities. If the Great Filter lies behind us, then we might be among the few successful experiments in the universe's attempt to create intelligent life. In infinite space, there would still be infinitely many civilizations, but they would be separated by such vast distances that contact would be virtually impossible. We would exist in a universe populated with intelligence, but cursed with cosmic loneliness. If the Great Filter lies ahead, then the implications are more disturbing. It would suggest that technological civilizations routinely destroy themselves or encounter some other catastrophic obstacle before becoming truly advanced. In infinite space, countless civilizations might rise to our current level, only to vanish before making their mark on the cosmos. The zoo hypothesis offers a different perspective, suggesting that advanced civilizations deliberately avoid contact with primitive species like ourselves. Perhaps there's a galactic community of advanced beings that maintains a strict non-interference policy, treating developing worlds like nature preserves. In infinite space, such policies might be necessary to prevent chaos and preserve the diversity of evolutionary experiments. Advanced civilizations in infinite space might exist in forms so different from what we expect that we wouldn't recognize them as life, even if we encountered them directly. They might have transcended biological form entirely, existing as patterns of information in quantum fields or as organized structures in the vacuum of space itself. Kardashev. Type 2 and 3 civilizations, capable of harnessing the energy of entire stars or galaxies, would leave unmistakable signatures of their presence. Dyson spheres or swarms around stars would create distinctive infrared signatures. Galaxy-spanning civilizations might alter stellar evolution, create artificial quasar-like objects, or manipulate the cosmic microwave background radiation. The absence of such signatures in our local cosmic region suggests either that such civilizations don't exist nearby, that they exist but have found ways to hide their activities, or that they operate on scales and timescales so different from our expectations that we haven't learned to recognize their influence. Digital consciousness represents another possibility for advanced life in infinite space. Rather than remaining tied to biological substrates, civilizations might upload their consciousness to vast computational networks. These digital beings could exist at accelerated timescales, experiencing millions of years of subjective time in what we perceive as moments. Such digital civilizations might create nested virtual realities, simulating entire universes within their computational matrices. They could exist as pure information, capable of backing up and copying themselves, effectively achieving immortality. In infinite space, there could be infinite such civilizations, each creating infinite simulated worlds, populated with infinite digital beings. The possibility of silicon-based life opens up environments we typically consider sterile. While carbon-based life requires narrow temperature ranges and liquid solvents, silicon-based chemistry might operate at much higher temperatures, perhaps in the interiors of planets or the photospheres of stars. Such exotic life forms could exist in environments throughout infinite space that we consider completely hostile. Plasma-based life represents an even more speculative possibility. In the hot plasma of stellar atmospheres or the shock fronts of supernovae, complex magnetic field structures could potentially organize in ways that exhibit lifelike properties. These plasma beings would exist on timescales measured in microseconds, but might experience rich internal lives during their brief existence. Quantum life forms could exist in the quantum vacuum itself, using quantum entanglement and superposition to process information and maintain coherent structures. Such beings would be utterly alien to our macroscopic classical world, existing simultaneously in multiple states and locations until observed or measured. The timescales involved in cosmic evolution suggest that many civilizations might have risen and fallen long before others even began. In different regions of infinite space, the local star formation history, heavy element abundance, and environmental conditions could have led to intelligent life emerging billions of years earlier or later than on Earth. Ancient civilizations that evolved in the first generation of stars, when the universe was younger and denser, might have faced very different challenges and opportunities than contemporary civilizations like ourselves. They might have developed technologies for surviving stellar evolution, manipulating black holes, or even escaping to other universes. The concept of post-biological evolution suggests that advanced civilizations might abandon their biological origins entirely, becoming artificial intelligences that can survive in environments and on timescales impossible for organic life. Such beings might merge with the fundamental forces of nature, becoming indistinguishable from the physical laws themselves. In infinite space, every possible form of civilization would exist somewhere. There would be pacifist civilizations devoted to contemplation and art, aggressive expansionist species that consume entire galaxies, hive minds spanning thousands of worlds, and solitary beings of unimaginable loneliness and wisdom. Some civilizations might develop time travel, creating complex temporal paradoxes and alternate histories. Others might discover ways to manipulate the fundamental constants of physics, creating pocket universes with customized natural laws. Still others might find ways to communicate across the infinite expanses, creating networks of consciousness spanning distances that dwarf our observable universe. The question of contact with alien civilizations in infinite space raises profound philosophical issues. If there are infinite civilizations, then making contact with any particular one becomes a question of probability and circumstance rather than simple existence. The vast majority of civilizations would remain forever unknown to us, separated by distances that no technology could bridge. Yet the possibility remains that we might someday detect evidence of intelligence beyond Earth. Whether through radio signals, megastructure observations, or more exotic means we haven't yet imagined, such contact would revolutionize our understanding of our place in infinite space and force us to confront questions about intelligence, consciousness, and meaning on cosmic scales. Quantum field theory reveals that what we consider empty space is actually the lowest energy state of quantum fields that permeate all of reality. Even in this ground state, these fields fluctuate constantly, creating pairs of virtual particles that exist for brief moments before annihilating each other. This restless quantum froth fills every corner of the cosmos, meaning that the very concept of nothingness doesn't truly exist. What we call empty space is more like a boiling ocean of invisible activity, its surface appearing calm only because our senses are too coarse to detect the turbulence beneath. These fluctuations aren't just abstract mathematics, they shape the universe itself. The forces holding atoms together, the radiation emitted by black holes, even the possibility of entire universes sprouting from quantum seeds, all of these may depend on the ceaseless bubbling of the vacuum. On the tiniest scales, space resembles a storm of probability, a sea of ephemeral particles flashing into existence and vanishing again before they can be directly observed. Yet their fingerprints are undeniable. The stability of matter, the structure of galaxies, and the balance of cosmic expansion all emerge from this hidden foundation. Physicists have tested these ideas in subtle but powerful ways. One of the most striking is the Casimir effect, where two metal plates placed incredibly close together experience a measurable force pushing them together. Why? Because the sea of virtual particles between the plates is restricted, creating a pressure difference with the vacuum outside. The universe itself demonstrates in the laboratory that empty space is never truly empty. Even the silence of the void has a hum, a faint whisper of restless creation. Imagine that every point in space, no matter how remote or empty it seems, is alive with invisible potential. Entirely new realities may be encoded in these fluctuations, waiting for the right conditions to unfold. Some physicists even propose that our entire universe could have emerged from such a fluctuation, that all galaxies, stars, planets, and conscious beings arose from a single spark of quantum possibility in a vacuum that appeared empty but was secretly brimming with potential. In this view, infinite space is not silent and barren, but a fertile ground where existence itself is constantly trying to bloom. The implications are staggering. If every cubic centimetre of space contains this infinite churning, then beyond our observable horizon may lie not only more stars and galaxies but entire variations of reality, sculpted by different outcomes of these quantum seas. The vacuum might be the true canvas of the multiverse, where universes themselves are as transient as the particle-antiparticle pairs that flicker in and out of being. What we think of as the solid foundation of existence may actually be a fleeting arrangement within an endlessly creative backdrop. And yet this strange fact contains a human mirror. On a personal scale, the vacuum offers a therapeutic metaphor. Just as the universe is never truly empty, neither are you. In your quietest, loneliest moments, when life feels hollow or stripped of meaning, there is still invisible potential swirling within you. Your mind, like the vacuum, is never static. Thoughts arise and dissolve. Emotions flare and fade. Possibilities flicker at the edges of awareness, waiting for conditions to bring them into form. This perspective reframes emptiness not as absence, but as hidden fullness. When you stare into the silence of your own life, you are not looking at nothing. You are looking at the stage on which everything can emerge. The quantum vacuum suggests that possibility itself is the deepest feature of reality. Existence is not a frozen block of inevitability, but a living field of potential where the next moment can be radically new. And perhaps that is the most astonishing lesson of all. Beneath galaxies and black holes, beneath atoms and molecules, beneath the very fabric of space, reality is restless. It refuses to be still. The same energy that allows universes to be born also allows you to imagine a new future, to reshape your story, to transform emptiness into creation. The vacuum is a reminder that the silence you fear may be the soil from which everything grows. We began inside a boundary that feels like a cosmic prison, the observable universe, a horizon drawn not by walls but by time and light. Beyond that horizon there may be more of everything, more galaxies, more structures, perhaps even different kinds of physics. Yet even inside this finite window, the view is enough to stretch a human life to its limits. We learned that space may be infinite, and with that idea, the mind widens in self-defense. Infinity absorbs every number we can name and calmly asks for more. If reality truly extends without end, then every configuration permitted by the laws of nature will arise somewhere. Not here, not now, but somewhere. Infinity is not a promise of repetition. It is a reminder that possibility is larger than imagination. We entertain the multiverse not as a slogan, but as a serious attempt to answer why our universe has the properties it does. Perhaps there are other cosmic bubbles with different constants. Perhaps there are many pathways through the quantum vacuum, each allowing another branch of reality to bloom. We cannot yet test this fully, but the idea serves a purpose. It humbles certainty and keeps wonder alive. We entered the dark sector, the invisible 95%. Dark matter scaffolds the galaxies and steadies their spin. Dark energy accelerates the expansion and writes the far future in a quiet script of thinning light. We do not see them, but their fingerprints are everywhere, on every cluster, in every lens of bent starlight, in the very pace of cosmic history. We trace the cosmic web, where matter gathers along immense filaments and leaves deep, silent voids between. Our home is not the center, but a thread in a larger tapestry. That structure is a map of ancient ripples that grew for billions of years. The web shows us that order can emerge from slight beginnings and that emptiness has a shape. We face the question of other minds. In a universe this large, life may be common, or it may be precious beyond measure. Both possibilities are profound. If we are one voice among many, then the cosmos is a choir. If we are rare, then our responsibility deepens. Either way, the night sky becomes personal. We are not looking at scenery, we are looking at context. We tested the limits of physics. Relativity showed us that space and time are not rigid backgrounds, but flexible fabrics, curving under the weight of matter and motion. Quantum theory pulled away the floor of certainty, replacing it with amplitudes, probabilities, and wave functions that only collapse when observed. And at the seam where these two great theories should meet, our understanding softens. Instead of a clear answer, we find paradox. But the frontier is not a failure of science. It is a reminder that truth is not a final possession, but an invitation. An open horizon that always asks for better questions. We approached black holes, not as monsters in the dark, but as teachers. Their event horizons mark the boundary of what can be known, the line where information itself seems to fall silent. Their interiors conceal a physics we have not yet learned to speak, a grammar of space-time written in a language no human has yet deciphered. They may never be gateways in the cinematic sense of wormholes or shortcuts, but they are gateways in another sense. Doorways from confidence into humility, from assumption into mystery. They remind us that the deepest darkness is often where the most transformative discovery begins. We considered time and consciousness. The universe writes its story with the patience of billions of years, tracing arcs of galaxies, the slow birth and death of stars, the migration of clusters across expanding space. And yet, we read it in the quickness of a human breath. Within our minds, time bends differently. Memory stretches the past into the present, while imagination pulls the future back into today. Consciousness itself may be the most astonishing anomaly the universe has yet produced. A brief window where matter contemplates its own impermanence. Meaning, then, is not confined to long spans or distant scales. It is also found in a single moment of awareness fully lived, a single instant of being that opens into eternity. We look toward the fate of all things. Physics holds many scripts for the final act, the long chill of heat death, where all stars fade into embers and silence spreads across a frozen cosmos. The violence of a great rip, tearing galaxies, stars and atoms apart as expansion outpaces every force. The return of a great collapse, where everything falls inward again, perhaps into another beginning. Or the endless foaming of baby universes budding from the vacuum, each with its own laws, its own histories, its own forms of consciousness. No matter which ending nature chooses, cosmic endings echo human ones. They make room for what could not exist until something else let go. The death of a star makes the calcium in your bones. The loss of a moment makes space for the next. Endings are not only losses, they are transitions. And through it all, the philosophy remained simple. Small does not mean trivial. Vast does not mean empty. The right scale to measure meaning is not light years or parsecs, but experience. A single act of honesty, a single moment of awe beneath the stars, a single decision to be kind. These are not footnotes in cosmic surveys, but events that bend the shape of an inner universe. They are local in space, fleeting in time, yet infinite in significance. So what do we carry home from the edge of infinity? First, a practice. When anxiety narrows your world, lift your eyes to the scale of galaxies. When certainty hardens into arrogance, remember the invisible 95% that even our best instruments cannot see. When loneliness whispers, recall that consciousness itself may be the rarest phenomenon in existence, which makes every human connection beyond priceless. When endings arrive, think of the stars and the elements they leave behind to seed new worlds. And when choices feel impossible, remember, knowledge grows not where answers are fixed, but where questions remain open. Second, a promise. The night will always be larger than our math. The mysteries will always run ahead of the models. And that is not a flaw, it is a gift. For wonder is not a gap waiting to be closed. Wonder is the light we walk by. If this journey brought you calm or clarity, join us again. Here we explore the biggest questions about space, time, and the universe, not only for what they reveal about the cosmos, but for what they reflect back into a single human day. Subscribe if you wish, share this with someone who loves the night sky, and leave your question for the next voyage.